All right, what's up, everyone? So last time we talked a little bit about span, and today we're going to talk a little more about span. But today's going to be more like how to visualize it and like doing stuff with actual numbers. Because last time I just showed that hey, a span was a subspace. But today we're going to play around with it, and we're going to try to really learn how to visualize these things, right? So this is the definition of span, right? You have span of v1 up until vk, you should read equal signs as is all linear combinations. Okay. Now, if you don't see the picture in your head, this isn't going to help. So let's talk about something that does help. And of course, what we always do is let's just do a bunch of examples, right? So in 2D, right, here's my favorite 2D example. I'm going to draw it for you. So let's look at a vector. I don't know, let's just pick a random vector. What's your favorite vector? Well, no one's going to answer me because this is a recording, but 2, 1. Let's talk about 2, 1. Okay, so the vector 2, 1 looks something like this, right? So here's the vector 2, 1. Let's call that V. Yep. And I want to study span of V. Okay. So very often in math, you're gonna come across these like definitions that are just like a little abstract and they don't really make sense. So what you have to do is go step by step and decipher it. And it might be the most painful thing in the world, but it will make perfect sense to you if you sit down and do that. So what is span, not spam, but span, of the vector 2, 1, right? What is this thing? Well, it's the collection of all c times the vector 2, 1, or a, or whatever your favorite number is, where that c is a real number. Okay, so this is the collection of all vectors 2c times c, where c is a real number. If you're still not sure what that looks like, then start picking random numbers, right? But I'm just going to tell you, this is the collection of vectors where the first coordinate is double the second, right? So just all multiples of 2, 1, right? So, okay, let's pick c to be 0, right? If c is 0, I get 2 times 0, 0, which is 0, 0. If c is 1, I get 2 times 1, comma 1. That's a times. So I get 2, 1, right? Among other things, we have vectors like 400, comma 200. That's on the list because the first coordinate, oh, left is on this. The first coordinate is double the second coordinate. 400 is double 200. You would pick c to be 200 there. I don't know, like minus 2 pi, comma pi, minus root 5, minus root 5 over 2, like 6, 3, literally anything where the first coordinate is double the second coordinate is on that list, right? Okay, so I've made you a big list and you can probably guess what else is in the span of this thing. Now, what does that picture look like, right? Well, you can, and think about why this is. I want you to sit down and think about why this is, but the span of this thing ends up just being the line pointing in that direction. And we talked a little bit about last time, but I want to reiterate. And the reason is because, well, here's 1.5. Here's like 1.5. And then you can just literally using all the numbers between 0 and 1, you can fill in this red line here and so on. And then you can fill in everything in the other direction using all the negative numbers and so on. I'm going to let you think about that, but just know that in one direction, if you have a span of one single vector, it's the line that vector points in. So let's write that down to reiterate. The span of one vector is the line the vector points in. Okay. Understanding this is very pivotal for understanding our next example, because now we're going to talk about what what it visually looks like to look at the span of two vectors, right? So for one vector, it was really easy, right? You had, let's say if this is V, right? This is V, then span of V is just everything in that same direction, right? Span of V. Okay, great. So now let's look at two vectors. Let's look at two vectors. So let's draw two vectors. And okay, so first let's try to interpret linear combinations. What does a linear combination look like, right? Well, you might remember something like if you have a starting point, if you have V1 and then V2, right? So this is V1 and this is V2. Well, then their vector sum is something that looks like this, right? You complete the parallelogram and then their vector sum is this new vector. Let's call that V1 plus V2, right? Okay, well now imagine you do the same thing, but I can scale it as much as I want. An example might be something like this, where I can take a third of V1 and I can take double V2 or something, right? Here's 2V2. So here's an example of a linear combination of V1 and V2, right? So something like that. Here's a third V1 plus 2V2. Okay, so I'm going to show you how to think about this. This is what the span of two vectors looks like. So let's draw my two vectors. Let's call this V1, or let's call this 2, 2. And let's call my second vector, let's call that, I don't know, 1 and 1/2. Okay, so here's how you think about the span of this thing, right? So first, we have the span of each vector just like automatically, right? We automatically get the span of each vector. So I can go as far in that direction as I want, and I can go as far in this direction as I want, right? Now, let's say, well, what if I started here on this line, right? This looks like 1/3 V1 or something, right? So 1/3 V1 plus something from V2. What does that look like? Well, adding something in V2 is the same as going in this direction, is it not? So if I start from 1/3 V1 and I add one copy of V2, that would look something like this, right? Well, that must also be in the span, so let's fill in that whole line. If I start from, say, maybe right here, then I fill in that whole line. That would look something like this, right? Literally, I fill in every single line pointing in this direction, starting from any random point on this pink line, right? So the pink line tells me how far I can go in the V1 direction if I scale V1. The green line tells me how far I'm going in the V2 direction, right? Well, you might notice you actually just get the whole plane, right? Like, you might notice this covers the entire plane. And that's exactly what happens, right? That's exactly what happens because if I just draw those two vectors again, right? And you can really visualize it this way. Well, I'm allowed to go as far in the V1 direction as I want. And then once I pick where to go, I can go as far in the V2 direction as I want. And any point can be obtained this way. Let's pick a random point, like right here, right? Well, what I would do is I would go so far back over here to the point where I can actually reach it. Oh, geez. Okay, I had to cheat a little bit. I'm sorry, I can't draw here. Let's move that point over a little bit. But you get the point, because I could have just gone farther in that direction. Yeah, so this is a multiple of V1, right? That pink vector right there, this vector is a multiple of V1 because it points in the v1 direction, right? So let's call that a1 v1. This green vector over here, this is a multiple of the v2 because it points in the v2 direction. So let's call that a2 v2. Well, that means that this point, which I literally called, like, I don't know, let's call that v3 or something. Well, then it must be equal to a1 v1 plus a2 v2. It's a linear combination of them because I was able to reach it doing a sequence of moves that point in each of those directions. So yeah, the span of this particular v1 and v2 I chose, comma 1 1/2, is indeed the entire plane, right? The entire plane. So any choice of point that you pick, we can get there, right? We can get there because you just, yeah, go in that direction. Okay, let's show that, right? Let's pick a random point. Let's pick an unlikely point, right? So like then any random point should be in this span, right? Which is the same as saying any point in R2 is a linear combination of 2, 2 and 1 1/2, right? Well, okay, let's show that. Let's pick a random point. I don't know. How about 0, 7, right? So then, if that were the case, then I'm going to start writing them as column vectors now. 2, 2 times some number plus b times 1 1/2. This is equal to, let's say, 0, 7, right? And I bet you I can find you a and b that do that. Okay, so this is the same as, I can just combine them, right? Let's see, 2a plus b and 2a plus 1/2 b, right, is supposed to equal 0, 7. Well, that's the same as saying the matrix 2, 2, 1 1/2 times the matrix AB is equal to 0, 7, right? Now, what do we know about this matrix right here? Let's calculate its determinant. Let's call this thing A. Well, the determinant of A is 1 minus 2, which is minus 1, which in particular means it's invertible, right? So because it's invertible, I can find you A and B that make this thing 0 and 7, right? In fact, 0 and 7 aren't even special because A is invertible. Any vector here has you can find A, B, right? So I can find you an A and a B where no matter what you try to do, or no matter what you put on the right-hand side, I can always find you an A and a B where if you multiply that matrix up to it. Okay, well, this is something important to observe. Notice this construction, right? We started with the vectors 2, 2 and 1 1/2. They ended up going like columns like this, right? So if you want to check, here's a really easy way to check if your set spans an entire space. So how do I check? How to check if your set spans entire space? Well, let's say you have n vectors and you're in n space. That's a really easy case, right? Write your vectors like this. v1, v2, ... like vn or something, right? If the matrix is singular, if this is singular, it does not span the whole space. If it's non-singular, it does. Now, this test only works when the matrix is a square. So that's the same as saying that it's invertible. Okay, so let's do one more example before we call it a day. Let's move on to 3 dimensions. So 3 dimensions. Because, well, our world's in 3D, and so, yeah, not that much of a point looking at anything else. So, okay, let's look at the span of 2 vectors in 3D, right? So let's draw my little 3D space, and let's draw my 2 vectors, right? Okay, well, this particular thing here, up here, what happened, right? I took one line, I extended it in both directions forever, and I just slid it along the other line, right? So if this is V1 and this is V2, I just took this whole line and I slid it up and down, right? And by sliding it up and down, it covers the whole plane. So we expect the span of two non-collinear vectors to be a plane. We expect that to be a plane because I take one thing and I take another one. Well, I'm allowed to slide this line up and down that other line. Well, if you look at the area that my arm is tracing through, it's tracing through a plane, right? So we would expect this to give us a plane. Here, just so that you have a better image of what this looks like. This is 0, 1, 1, and this is the vector 1, 1, 0, right? Okay, well, let's just repeat that construction, right? So I can do, here, I'm gonna take this green line and I'm just gonna copy paste it a bunch of times along this red line, right? And look what it's doing, look what it's doing. Look at the shape it's tracing out, right? In fact, okay, it actually goes up way more than that, but like, I'm gonna put dotted lines there to show you that this plane keeps on going. But yeah, it's it kind of gives us this plane over here with this dark blue shadow, right? So actually, I'm just gonna show it in. So yeah, the span of 2 vectors is this plane. It does go on in every direction and it extends below the xy plane as well. But yeah, the span of these 2 vectors in particular is this plane. Okay. Okay, so you're probably asking me, why do you care about this, right? Why do you care about this? Well, the idea is, let's say I have a vector space V, right? Let's say I have some vector space V. And all of a sudden, you just found some random subspace in here. Here is a subspace that might be a little hard to describe. Right, here's a subspace, which of course contains the 0 vectors. So there's 0. Okay, there's a subspace. I want to be able to describe this subspace. I want to be able to work with this subspace, right? So, but in particular, I would love it if I could find a way, because this looks an awful lot like a plane, right? So I want to find a way to give me quote unquote coordinates on that plane, right? So I want to find a meaningful way to assign coordinates on that plane to this one, right? Like compared to this one. So for example, if that's 0, 0, right? And I found you 2 vectors like V1 and V2 or something, right? I don't know, this is a really contrived example. Well, if I found you that, then those 2 things actually span the whole plane, right? Those 2 vectors span the plane. Okay, that's great. Then I can write every point. The idea is to say, here's a random V, right? Let's say this is V. Let's use a brighter color so you can actually see. There, that's V, right? So you have this vector V, which is some linear combination of V1 and V2, right? Well, then what I'm going to do is I'm going to put this in bijection with the point A1, A2. That lives on this plane, right? So I find a point, let's call that A1, A2. And this is the V1 axis. and this is the V2 axis. Notice this looks a lot like a plane, right? So then math here is easy. Math here is hard, right? So the idea is you want to find a spanning set that you can spell all of your vectors with these like coordinates, right? Well, if you have coordinates, you can study what happens on just this plane. You do math on the really easy plane, and then that must translate to something happening back in this other wild subspace you have. So that's one of the reasons why you might study spans, right? It lets you decompose it, and then it lets you do math maybe in simpler terms. Later on, you're going to learn about this thing called change of basis, which is exactly what I've described here. But there's another problem that I haven't talked about, which is like you'll notice I said two vectors span a plane, right? Well, what if I looked at the span of V, V1, and V2? What if I looked at the span of these three vectors, right? Because they all live in the same plane, well, the span is still the same plane. And unfortunately, if that's the case, you don't have a unique way to assign coordinates, and that's what we're going to talk about next time. We're going to talk about linear independence, which is the condition that you need to assign unique coordinates. Okay, I'm going to peace out, and I'll like see you in the next thing, whatever. All right, bye.